Thank you, Mr. Donahue, for the nice introduction, and good morning, everyone. So you have heard from the previous speakers sort of bigger picture view of all the regulations the industry is dealing, and also the direction, the big direction the industry is taking. So I'm going to sort of get into the smaller area of water, but more specifically wastewater, how to eliminate the wastewater completely, hopefully with our solution. Then, as the chairman mentioned, Bob Nicolo, who was originally scheduled to be here, could not make it this week, so I'm the backup. Bob and I are both from Mitsubishi Hitachi Power Systems, the office in Basking Ridge, New Jersey. We are responsible for all the environmental solutions and also combustion and solid fuel solutions. So in the next 20-some minutes or so, I'm going to try to give a very brief overview of the regulation background and impact of the regulations, specifically the ELG and the CCR regulations. And also, what are the compliance options for these new regulations? And then finally, introduce a solution, which is the wastewater spray dryer, or WSD, which is a zero liquid discharge solution that eliminates really the wastewater stream. So first, let's take a look of what is what's in the effluent limitation guidelines and the coal combustion residual rule. These are the two most recent regulations the industry is dealing with. This is a high-level overview of the ELG that was released last September, was finalized. It has been a long time since 1982 was the last time EPA had the last ELG guidelines. And the last ELG guidelines were really outdated. You're talking about controlling only the suspended solids and oil and grease, simple control like that. But the new guideline, I have to say, is very advanced in terms of technology requirement and very stringent in terms of limits. It covers all the wastewater streams in a power plant with very strong focus on mercury, arsenic, selenium, and very, very strong focus from the wet scrubber discharge. The compliance period is from November 2018 to end of 2023. I will explain later, power plants have the options to choose the more stringent option, which allow you more time for compliance, meaning you can go all the way to 2023 for the compliance if you choose to go the more stringent option. And also another important thing is this ELG goes hand in hand with the CCR rule. CCR is the coal combustion residual. Really the heavy focus is, many plants, we use these impoundment or simply ash ponds to keep the ash, water, etc., from the boiler itself and also from the FGD and other operations. But you can see many of these are going to discontinue into the future under CCR and ELG, because CCR has faster timelines. So in fact, some of the ELG solutions will be implemented before the ELG deadline, rather due to the CCR requirement. So these are, I don't expect you to read those fine prints. This is taken directly from the EPA document. It's a 600-page document, but these are all the ABCD EFG EF is all these options that EPA looked at when they would prepare the draft for this regulation. And at the end, in the final version, in the final version, they pick option D. In the option D, again, the heavy focus on wet FGD wastewater. For wet FGD wastewater, this base option requires FISCAM treatment plus FISCAM treatment followed by biology treatment. I will have some pictures to show you what they are. But that's the base option for FGDs. And then for other water streams like fly ash transport and bad ash, bottom ash transport, the solution is going dry. So if you have a wet transport system, you need to convert to a dry system. Or otherwise, if you can use that water in FGD or somewhere, then it's okay as well. So then option D is a base option, but EPA also allow you to use the evaporation route, which is option F, in which case you have a more stringent set of limits, and you will have a few more years in the compliance schedule. And the solution I'm going to talk about later, the zero liquid discharge solution, will qualify you for this extension of for compliance. Just to give you a flavor of the numbers themselves, very stringent standard. First, this arsenic, mercury, selenium, nitrate, nitrate were not in the original 1982 guidelines. They are new, and in fact, we are probably the first country in the world to have some of these elements to control to these levels. Then you look at the numbers themselves. The arsenic and selenium, we're talking about parts per billion levels, and nitrate, nitrate parts per million levels. But mercury, we're actually taking to the parts per trillion level. Of course, these are very, very low levels. And then another way to look at it is if you look at what's in FGD and what it takes to meet these new limitations, you are looking at 98 and 99 plus removal of these elements. Another way to look at it, all these numbers, the daily average, a monthly average actually, are actually below EPA's current drinking water limits of these same elements in drinking water. So you can tell this is extremely stringent and demands really new solutions. What would be the impact of this, these ELG and also combined with CCR regulations? Here's a table of the affected units. This is per EPA. There's currently 150 power plants that have operating wet FGDs. That represent 367 generating units. These are not units of wet FGDs, rather these are number of generators in these plants. Since some of these generators or units combined, you share a FGD, or some may have two FGDs for one unit. So really the number of FGD units is 311 in this country, total wet FGD. I'm not talking about dry units. Dry FGDs does not produce wastewater, therefore it's not a concern here. And also wet is more than 80% of all the FGDs in this country. So 311 wet FGD systems. On average size close to 500 gigawatt apiece, they need to take care of their wastewater. All these FGDs really covers most part of the country, maybe more heavily in the east part of the country, because in the eastern part of the country we tend to use historically the bituminous coal, which is typically higher in sulfur. Therefore, they are the first units to get scrubbed. Again, the average size of these units are about 500 megawatts. Now, today, even some of the eastern part of the FGDs are actually burning PRB coal because they become available. In terms of price, very competitive. But historically, they were designed for higher sulfur coal. What about the cost? We talk about 311 units needs some sort of wastewater treatment. In terms of cost, this is the study by EPA and also EPRI for a sample of 116 power plants. Now, the total number of plants affected is 150, so 116 is only not a complete sample, only two-thirds of the, more than two-thirds of the all the plants. And for this 116 plants, the cost is going to be per EPRI. Per EPRI, it's going to be $5 billion just to put in FISCAM treatment, the basic treatment. But to meet the requirement of ELG, you need to put chemical precipitation of FISCAM treatment followed by biologic treatments. And that it would take $7 billion for this 100 CapEx, $7 billion CapEx for this 116 facilities. So if you extrapolate to 150 plants, that's going to be $9 or $10 billion, roughly the impact of CapEx to the industry. So with that impact, what are the options the industry have? Let's first take a look, where this wastewater coming from in a plant with wet FGD. You can see on the left side is just a 3D picture of wet FGD. You have the flue gas coming in from the very left-hand side bottom, and then goes through several stages of sprays of, so the limestone slurry is sprayed, impact almost every molecule of the flue gas, and that's how it gets cleaned. And there's typically modern scrubbers has 4, 5, or even 6 stages of sprays to take some of the pollutant level like SO2. It's quite common reduction will achieve 98 to 99% plus levels. So it's not surprising to see many power plants to have single-digit ppm emissions in SO2 from these plants. And on the right-hand side, you can see 3 stages of this FGD system. The first part is reagent preparation. There, basically, you pulverize the limestone, and then you turn the limestone into a slurry that is 70–80% water and 20–30% limestone. And then in the scrubber, you inject that limestone into the multi-layers of the sprays to capture pollutant. Now, not only SO2 is captured, that's the main purpose of the scrubber, but only all the heavy metals and acid gas like hydrogen chloride, they are captured. And therefore, these things build up, especially chloride. It's a challenge. It's caused corrosion. So these scrubbers can build up 1,000 ppm or tens of thousand ppm of chloride levels. Therefore, you have to design with some alloy material, corrosion-resistant material, to control this corrosion. And also, you have to control the level of chloride level concentration in the scrubber. You're doing that by, in the next stage on the right-hand side, you can see the dewater stage. Dewatering is basically separation of the water from the byproduct of scrubbing, which is gypsum. So the separated water, you bleed some of that water. That allow the blowdown. That allow you to control the concentration of chloride in the scrubber, therefore to prevent corrosion. So for this FGD wastewater, what are the options we have? If you look at the EPA, their proposed solution is, as I mentioned, the base solution is a phase chem treatment followed by biologic treatment. And the option is vapor compression, evaporation, plus crystallization. What we propose is an alternative approach that has two steps. The first step is we will support people with FGDs, customers, to first optimize their operation, to reduce the blowdown, the volume of that wastewater in terms of gallons per minute. Because with the new control requirement, every gallon per minute is going to cost you so many millions of dollars in the long run. So you have to do the calculation, have to reduce that flow. Sometimes we often see the customers have the scrubbers designed to handle high level of chloride and allow a low blowdown wastewater level. But some part of the system, it could be just one small pump that's not built with the good alloys to take the corrosion. Therefore, you may have to consider replace some components to allow you to operate at a higher level of chloride and therefore reduce the volume of wastewater. And after we optimize the operation of the FGD and minimize the volume of the wastewater from these FGDs, then the next step our solution is simply to evaporate it, to eliminate this wastewater stream completely. So some more graphics on these solutions. This is part of the base solution, and some, I think about 30% of power plants in this country already have this phase chem treatment system. This is a very mature technology. Many of us are very familiar with it. Involves multiple tanks. Some are storage tanks and some are reaction tanks. And multiple steps of chemical reagent is added. Most commonly, lime is added to neutralize this wastewater, and also to desaturate the solids, dissolved solids, some gypsum, desaturate that to allow following stages of operation. Then other additives are added to take out metals and heavy metals and other things. So it's a multiple step system. It involves some of the, it involves significant operating costs because of reagent and also the operating care. Operators, full-time operators needed. And it's not able to meet the ELG requirement by itself because it cannot take out selenium and the nitrate. So this is the base option by EPA, which is essentially the phase chem system followed by a biologic system, and which is, as you can see, another multiple reaction tank system and the storage tanks, the recirculation pumps, etc. In a biologic system, you basically try to keep the microbes alive with the correct temperature, pH, and oxidizing conditions, and feed the necessary nutrient to keep these bugs alive to convert selenium and nitrate into elemental forms so that you can take them out in the solid waste. So it's a rather complex two-step and a multiple reaction tank system, and obviously it's rather costly in terms of CapEx and also OpEx. And another thing is it's not able to achieve zero liquid discharge. So people are wondering, what if EPA come up with even more stringent requirement? Then you may have to add some more to the system. So the next is the alternate approach by EPA, which is evaporation approach. This is a ZOD solution. Uses vapor compression thermal evaporation system followed by crystallizers to get rid of the wastewater. But again, as you can see, this involves rather complex unit operations. It also involves high-grade alloy material. In many cases, you're talking about either alloy or titanium, the expensive options like that. And involves very stringent operations requirement. So, and the cost overall is even more expensive than the base system of Physchem Bio. So that leads to the solutions that I'm describing. And first, a little bit background of our ZLD solution, the zero liquid discharge. Started in the 1980s, Mitsubishi Hitachi Power System has built 10 commercial systems in Japan to achieve ZLD by simply inject the wastewater from the Wet FGD into the flue gas duct between the air preheater and the ESP, where the temperature is about 300 degrees Fahrenheit. It's simply injecting into the existing duct, and it's using dual fluid atomizing, and the wastewater is dried, and all the residual and the water vapor is combined with the flue gas and fly ash end up in the ESP or baghouse. This, as I mentioned, has been installed in Japan on 10 units, and we learned a lot of experience in terms of how to spray, how to atomize the wastewater, and how to make sure it's dry. But it's not universal solution because most of the plants, especially our existing fleet in the US, we don't have a lot of space and a lot of duct lengths to allow complete drying of this wastewater in the existing structure. Therefore, based on that knowledge, we developed this variation of what we call the wastewater spray dryer, WSD. In this solution, instead of injecting into the main flue gas duct, we are taking a slipstream of flue gas from somewhere between the upstream of the air preheater, downstream of the SCR, downstream of SCR and upstream of air preheater. We take a small slipstream, which is hot at about 700 degrees Fahrenheit. We use that as a heat source to evaporate the wastewater in this wastewater spray dryer, which is really based on the spray drying technology, which is many decades old. It's probably one of the oldest technology in the chemical engineering area. So we're basically using that technology to evaporate the wastewater in that spray dryer. A little bit about development, how we develop this process. First is based on drying research. As I described, we are atomizing or basically turn this water into small droplets. And when they dry, they go through actually 5 steps of drying process. Essentially, first is fast heating. Then it started some drying and it forms a crust because of the dissolved solids in these droplets. And this crust prevents heat transfer and slows down drying and also further heat transfer. So it's a crust formation and then followed by the slow drying process. And the rate of the drying is depending on how much solids is dissolved in this wastewater. So we did a lot of fundamental research in this area and developed models for predicting this process, and combined with a pilot plant testing of rather large-scale pilot plant, and then we developed modeling programs to combine the single droplet research with pilot plant and to help us design the full-scale units. This is basically showing that with the CFD we are able to simulate the particle size, temperature profile, and drying history of all the testing with the simulation program that help us to scale up to full-scale unit. And today we're able to offer a full spectrum of commercial sizes, as small as 10 or 15 gallon per minute to as large as over 200 gallon per minute, a single unit. This is to show the key elements of the WSD, which is atomizer. We are seeing rotary atomizer here. On the left-hand side, you have a single atomizer arrangement, and on the right-hand side, it's a larger spray dryer with 3 atomizer arrangement. These are actually, with these atomizers has variable speed drives, rotating at 12,000 to 15,000 RPM, a very high rotation energy. That's what helps pulverize the water into small droplets. And what's showing in the middle is a picture of this atomizer, which is rather small. It's like a little bit bigger than a 5-gallon bucket. It weighs about 250 pounds. Relatively easy to remove and replace, and you can do the replacement even during the operation. This is to show an example of this system for a 600 megawatt boiler. The added red part is the added system for WSD or ZLD. Here, basically, you're taking the dewatering wastewater and pump into this spray dryer. Sometimes, usually there is a surge tank in between, and the wastewater goes into the spray dryer and taking the slipstream hot gas as a heat source to evaporate this wastewater. In this case, a 600 megawatt units treating 88 gallon per minute of wastewater. We're taking 8.6% of the flue gas from this boiler at about 660 degree Fahrenheit temperature. And after drying, we are sending back a little bit more because you turn the water into water vapor, so you're adding about 1.2% of flue gas volume, sending it back to the ESP, the existing ESP, and also adding a few percent, less than 5% of the solids, because you do dry the solids from the wastewater into the ESP. I should also mention this spray dryer, the little thing there in the red, is all of carbon steel construction. So it's a really low-cost solution. There's not much to it. Some ducts, some pumps, and a carbon steel vessel, and with some rotary atomizer. Okay, another way how to take a look. This is a simple GA to show you, and also a very simple equipment list. There's really not too many major equipment. You see the list is very short. We have inlet and outlet of the slipstream. We have isolation dampers, so to make sure this water evaporation system doesn't have to be running. It can be totally isolated easily from the main plant for low load or for other conditions. Then there's the rotary atomizers, in this case 3, and the vessel itself, and wastewater holding tank or receiving tank, and also agitators and the pumps. That's all there is. And this is a 3D image of a design we did for a recent customer here in the US. What you can see is the WSD is taking the flue gas from basically the SCR outlet, and then treat it, dry it, and sending the flue gas back to the baghouse. The baghouse collects the existing fly ash together with the drying residue. Okay, that brings us to the summary. Basically, this is a very flexible and simple and economic system. And that is, we think it's a good alternate solution compared to what EPA has proposed. Either it's a phase chem plus bio or a evaporation plus crystallizer solution. And compared to those, this is a very simple solution that can be implemented to achieve ZLD for your plants. Thank you.